the story of a cosmic mystery. In the constellation Hercules, there's a place you can't see with your eyes, a cluster of galaxies, hundreds of them, floating together in the darkness. At first glance, it seems like any other galaxy cluster, massive, ancient, bound by gravity into a single cosmic family. But look closer, and something strange emerges. The central galaxy, the brightest one, the one that should anchor the entire cluster, has a secret. Its core is empty, or at least it appears that way, where there should be a supermassive black hole, billions of times the mass of our sun. There's nothing, or nothing we can find. Astronomers have searched. They've used the most powerful telescopes in the world, instruments that can see across billions of light years, detect the faintest whispers of X-rays, map the motions of stars with incredible precision, and still, the black hole eludes them. This is the story of Abell 2261, a mystery wrapped in starlight, a cosmic detective story playing out across the universe. A cluster hidden in the depths of space. Abell 2261 isn't nearby. It's not something you can point to in the night sky and say, there it is. It sits over 2 billion light years from Earth, so far away that the light we see left that cluster long before humans existed, before our solar system even formed. It's hidden in the depths of space, one of thousands of galaxy clusters scattered throughout the observable universe. But what makes it special isn't just its distance, it's what lies at its heart, or what doesn't lie there. Most galaxy clusters have a central dominant galaxy, a massive elliptical that formed through countless mergers over billions of years. And at the center of that galaxy, buried deep within the core, there should be a supermassive black hole. That's the pattern. That's what we've found everywhere else. But Abell 2261 breaks the pattern. Its central galaxy has a core, yes, but the core is strange, puffy, diffuse, and apparently empty. The light that traveled billions of years, the light we see from Abell 2261, is ancient. It left the cluster over 2 billion years ago, when Earth was in the Proterozoic eon, a time of simple life and quiet oceans. That light traveled across the expanding universe, crossing vast cosmic voids, passing countless other galaxies, until finally it reached our telescopes. Every photon is a messenger from the past, carrying information about conditions in the cluster as they were billions of years ago. When we study Abell 2261, we're not seeing it as it is now, we're seeing it as it was, frozen in time by the speed of light. The cluster has continued to evolve since then. Stars have been born and died, galaxies have merged, the structure has changed, but we'll never see those changes until billions of years in the future. The light that traveled billions of years connects us to a distant past, a window into cosmic history, the vastness of the observable universe. To understand Abell 2261, you have to understand scale. The universe is vast, almost incomprehensibly so. The observable universe extends about 93 billion light-years across, filled with billions of galaxies, each containing billions of stars, and scattered throughout this vastness are galaxy clusters, the largest gravitationally bound structures in existence. Abell 2261 is one of these, a collection of hundreds of galaxies, spanning millions of light-years, containing more mass than 1,000 Milky Ways. It's enormous, but in the context of the entire universe, it's just a dot, one cluster among millions, maybe billions. And yet that single cluster contains mysteries that could reshape our understanding of black holes, galaxy formation, and the fundamental forces that govern the cosmos. Size doesn't determine importance. Sometimes the most profound questions come from the smallest, most distant places, or in this case, the most distant mysteries. The discovery of Abell 2261. Galaxy clusters aren't discovered by accident. They're found through systematic surveys, careful observations, and years of cataloging, Abell 2261 was identified as part of one such survey, a project that mapped the distribution of galaxies across the sky. The cluster stood out because of its richness, the sheer number of galaxies packed into a relatively small region of space. It was cataloged, given a number, and added to the growing list of known clusters. For years, it was just another entry in astronomical databases. Another distant cluster, interesting, but not particularly unusual. But then astronomers started looking closer. They began studying the central galaxy, measuring its properties, mapping its structure, and they found something unexpected. The core was different, larger than it should be, diffuse, and when they searched for the central black hole, they couldn't find it. That's when Abell 2261 went from being just another cluster to being one of the most intriguing mysteries in modern astronomy. The astronomer who cataloged the cluster. The name Abell comes from George Abell, an American astronomer who spent years cataloging galaxy clusters. In the 1950s, Abell painstakingly examined photographic plates from sky surveys, identifying clusters by eye, measuring their richness and distance. His catalog, published in 1958, contained over 4,000 galaxy clusters and became a foundational reference for astronomers. Abell 2261 is one of those entries, a cluster identified by Abell's careful work decades ago. George Abell never knew about the mystery at this cluster's heart. He couldn't have. The technology didn't exist to study distant galaxies in the detail we can today, but his catalog made it possible. By identifying and classifying these clusters, Abell gave future generations of astronomers a roadmap, a guide to the largest structures in the universe. His legacy lives on in every study of galaxy clusters, in every observation of distant cosmic structures. Abell 2261 is named for him, a tribute to the astronomer who mapped the universe's grandest architecture. The legacy of George Abell's Cosmic Atlas. Abell's catalog wasn't just a list. It was an atlas, a map of the universe's large-scale structure. Before Abell, astronomers knew that galaxies clustered together, but they didn't have a systematic understanding of how common clusters were or how they were distributed across space. Abell changed that. His catalog showed that galaxy clusters were fundamental building blocks of cosmic structure, nodes in the vast web of galaxies that spans the universe. The catalog has been refined over the decades, with new observations and better distance measurements, but its core remains unchanged. Abell clusters are still studied, still referenced, still central to our understanding of the universe, and some of them, like Abell 2261, continue to surprise us, revealing mysteries that Abell himself could never have imagined. His cosmic atlas was just the beginning. The real discoveries came later, as astronomers began to explore the clusters he'd identified, uncovering secrets hidden in the depths of space. The family of galaxies, bound by gravity. A galaxy cluster is more than just a collection of galaxies. It's a family, bound together by gravity, into a single coherent structure. In Abell 2261, hundreds of galaxies orbit a common center, held in place by the combined gravitational pull of all the mass in the cluster. Some of these galaxies are massive ellipticals, bloated giants formed through countless mergers. Others are smaller spirals, still forming stars, still evolving, and scattered throughout are dwarf galaxies, tiny collections of stars that orbit the larger members like moons around planets. They all move together, a complex dance, choreographed by gravity. Over time, some galaxies will merge, combining their stars and gas into larger structures. Others will be torn apart by tidal forces, their stars scattered into the space between galaxies. The cluster is dynamic, constantly evolving, shaped by the gravitational interactions of its members. It's a family, but a chaotic one, held together by forces that are both creative and destructive. The enormous scale of a galaxy cluster. Galaxy clusters are enormous. Abell 2261 spans several million light-years, a distance so vast that light takes millions of years to cross from one side to the other. If you could somehow stand in the middle of the cluster, galaxies would surround you in all directions, each one a distant island of stars, separated by vast gulfs of nearly empty space. But that space isn't entirely empty. It's filled with hot gas, plasma, heated to tens of millions of degrees by the gravitational energy of the cluster. This gas is invisible to optical telescopes, but glows brightly in X-rays. And threaded through everything is dark matter, the invisible substance that makes up most of the cluster's mass. The scale is hard to grasp. Our entire Milky Way galaxy would be just one small member of this cluster, dwarfed by the giant ellipticals at its core, and the cluster itself is just one of many, a single node in the cosmic web that fills the universe. The core that holds it all together. At the center of Abell 2261, there's a core, not a physical core like the Earth's iron center, but a gravitational one, a region where the density of galaxies is highest, where the pull of gravity is strongest. This core is the cluster's heart, the anchor around which everything else orbits. In most galaxy clusters, the core contains a single dominant galaxy, the brightest cluster galaxy, or BCG. This galaxy sits at the gravitational center, having grown massive through billions of years of cannibalizing smaller neighbors. And at the center of that BCG, buried deep within its core, there should be a supermassive black hole, the remnant of countless mergers, a gravitational monster that helps regulate the cluster's evolution. That's the pattern we see everywhere. But in Abell 2261, something is different. The core is there. Yes, the BCG is there. But the black hole? That's where the mystery begins. The central galaxy of Abell 2261. The central galaxy of Abell 2261 is a giant. It's a massive elliptical galaxy, the brightest in the cluster, sitting at the gravitational center. This galaxy formed through mergers, countless smaller galaxies falling into the center over billions of years, their stars and gas absorbed into the growing giant. It should look like other BCGs, a smooth, featureless glow, densest at the center, fading gradually toward the edges. And in most ways, it does. But there's something unusual. The core of this galaxy, the innermost region, is enormous, much larger than it should be. Most elliptical galaxies have dense cores, regions where stars are packed tightly together, orbiting around the central supermassive black hole. But this galaxy's core is diffuse, spread out over a region tens of thousands of light-years across. It's as if something scooped out the center, leaving behind a puffy, low-density core. Astronomers call it a core deficit, a region where stars should be but aren't, the brightest cluster galaxy ever seen. Among galaxy clusters, Abell 2261's central galaxy stands out. It's one of the brightest cluster galaxies ever observed, glowing with the combined light of trillions of stars. BCGs are typically the largest and most luminous galaxies in their clusters, but this one is exceptional, even among BCGs. It's a beacon, visible across billions of light-years, a testament to the power of gravitational assembly. But brightness isn't the only thing that makes it special. It's the structure that sets it apart, that enormous diffuse core, the absence of the expected central concentration of stars, the mystery of the missing black hole. This galaxy should be a typical BCG, following the patterns we see in other clusters. But it's not. It's an outlier, a puzzle, a galaxy that challenges our understanding of how these massive structures form and evolve. And that's what makes it so fascinating. The strange, puffy heart of the giant. The core of Abell 2261's central galaxy is strange. Instead of being dense and compact, it's diffuse and extended, stretching across tens of thousands of light-years. This isn't how galaxy cores usually look. Normally, the densest concentration of stars is right at the center, where the supermassive black hole sits. The stars there orbit the black hole, packed tightly by its immense gravity. But in this galaxy, the core is puffy, as if something pushed the stars outward, creating a hollow center. Astronomers have measured the size of this core carefully. It's about 10,000 light-years across, roughly 10 times larger than typical cores in galaxies of similar mass. That's extraordinary. And it suggests that something dramatic happened here. Some event, some process, that rearranged the stars, creating this unusual structure. The question is, what? What could cause a galaxy's core to become so diffuse? The answer might lie in the missing black hole, the diffuse glow of ancient stars. The stars in the core of Abell, 2261 Central Galaxy, are old, ancient, red giants and fading dwarfs. Stars that formed billions of years ago when the galaxy was young. They glow with a soft golden light, the light of age and stability. These stars have been orbiting the galactic center for eons, following paths shaped by gravity, by the presence or absence of a central black hole, and their distribution tells a story. The way they're spread out, diffuse rather than concentrated, suggests that something disrupted their orbits long ago. If a supermassive black hole was ejected from the galaxy's center, the stars would have responded, their orbits expanding, the core growing larger. It's like removing the central anchor from a system. Without the black hole's gravity to hold them in tight orbits, the stars would drift outward, creating the puffy core we see today. The diffuse glow is evidence, a clue in the cosmic mystery. The structure, unlike any other galaxy. Most massive elliptical galaxies follow a pattern. They have dense cores, smooth profiles, and a clear concentration of light at the center. But Abell 2261's central galaxy breaks the pattern. Its structure is unusual. Unlike other galaxies of comparable mass, the core deficit, the diffuse stellar distribution, the absence of a detectable central black hole, all of these features set it apart. Astronomers have compared it to other BCGs, looking for similarities, searching for other galaxies with similar structures. They've found a few, but they're rare. Core deficits exist in some massive ellipticals, usually in galaxies that have undergone major mergers. But none are quite like this. None have cores this large, this diffuse, combined with such a complete absence of a detectable black hole. Abell 2261's central galaxy is an outlier, a unique structure that challenges our models of galaxy formation and evolution. And that makes it invaluable for understanding the extremes of cosmic processes. The secrets hidden in its core. What secrets lie in the core of Abell 2261's central galaxy? That's the question driving astronomers. The core holds clues about the galaxy's history, about past mergers and violent interactions. It might reveal what happened to the central black hole, if it ever existed, and it could teach us about the physics of galaxy cores, about how stars respond to dramatic gravitational events. By studying the stellar distribution, astronomers can model the galaxy's past, running simulations to recreate the conditions that could produce such a structure. They look at the velocities of stars, their orbits, their ages and compositions. Every piece of data adds to the picture, and slowly, a story emerges. A story of collision, of merging galaxies, of black holes spiraling together, and perhaps kicking one out entirely. The secrets are hidden, yes, but not lost. They're written in the positions and motions of billions of stars, waiting to be read. The search for the missing black hole. The search began when astronomers realized something was wrong. Every massive galaxy should have a supermassive black hole at its center. That's what theory predicts. That's what observations confirm. Again and again. But in Abell 2261's central galaxy, the black hole couldn't be found. No X-ray emission from hot gas falling into it. No radio signals from jets. No signature in the motions of nearby stars. It was as if the black hole didn't exist. But that seemed impossible. A galaxy, this massive, formed through so many mergers, should have a black hole weighing billions of solar masses. So astronomers launched a search. They turned the Hubble Space Telescope toward the galaxy, mapping its structure with exquisite detail. They used the Chandra X-ray Observatory to search for the telltale glow of an active black hole. They combed through radio observations, looking for any sign of activity, and they found nothing. The black hole, if it exists, is silent, hidden, or gone. The black hole that should be there. Theory is clear. Massive galaxies form through mergers, smaller galaxies combining over billions of years. And when galaxies merge, their central black holes merge too, spiraling together until they coalesce into a single, more massive black hole. This process has been going on since the early universe, building supermassive black holes up to billions of times the sun's mass. Abell 2261's central galaxy should be no exception. It's a massive elliptical, clearly formed through numerous mergers. It should have a black hole at its core, one of the largest in the universe, perhaps weighing 10 billion solar masses or more. That black hole should be detectable. Even if it's not actively feeding, it should influence the motions of nearby stars. If it is feeding, it should emit X-rays, radio waves, visible light, but we see none of that. The black hole that should be there isn't, or at least we can't find it. And that's the mystery. The empty center that defies expectation. The center of the galaxy appears empty, not physically empty. There are stars there, gas, dust, the normal components of a galaxy core. But gravitationally, it seems hollow. There's no dense concentration of mass at the very center, no supermassive black hole dominating the gravitational field. This defies expectation. It contradicts everything we know about how massive galaxies should look. Astronomers have searched the central region repeatedly, using different instruments, different wavelengths, different techniques, and every time, the result is the same. No black hole, or at least no detectable black hole. This empty center is puzzling. If the black hole isn't there, where did it go? Was it ejected somehow, flung out of the galaxy by some catastrophic event? Or is it there but dormant, so quiet that we simply can't detect it? Both possibilities are intriguing, and both have profound implications for our understanding of black holes and galaxy evolution. The mystery that puzzled astronomers. When the first studies of Abell 2261's central galaxy were published, they sparked debate. How could a galaxy this massive not have a detectable black hole? Some astronomers questioned the observations, suggesting that the black hole might be there, but obscured by dust, or simply too faint to detect with current instruments. Others proposed that the galaxy's history was unusual, that perhaps it never formed a very massive black hole in the first place. But most astronomers were intrigued by a third possibility, one that seemed almost science fiction. What if the black hole had been ejected, kicked out of the galaxy entirely by the recoil from merging with another black hole? This idea, once purely theoretical, suddenly had a potential real-world example. The mystery puzzled astronomers because it challenged fundamental assumptions. It forced them to confront the limits of their models and observations, and it opened up new questions about the most extreme processes in the universe. The clues from the Hubble Space Telescope. Hubble's sharp vision revealed the first detailed look at the galaxy's core. The images showed the unusual structure clearly: the large, diffuse core, the lack of a central concentration. Hubble could resolve individual star clusters around the core, allowing astronomers to study their properties and motions. By mapping the distribution of light with exquisite precision, Hubble provided crucial data for understanding the galaxy's structure. The telescope also searched for signs of a displaced black hole. If the black hole had been kicked out but remained within the galaxy, it might be visible as a concentration of stars orbiting an invisible massive object. Hubble looked for such concentrations in the outer regions of the core, areas where a recoiling black hole might have ended up. The search was painstaking, analyzing the motions of thousands of star clusters, And while Hubble didn't find the black hole, it provided invaluable clues about where it might be or where it isn't. The follow-up from the Chandra X-ray Observatory. If the black hole was actively feeding, it should emit X-rays. Gas falling into the black hole heats up to millions of degrees, glowing brightly in high-energy radiation. Chandra, NASA's X-ray telescope, is designed to detect exactly this kind of emission. So astronomers pointed Chandra at Abell 2261's central galaxy, searching for the telltale X-ray glow of an active black hole. They observed for hours, gathering data, looking for any sign of activity, and they found the cluster's hot gas, glowing in X-rays, filling the space between galaxies. But in the galaxy's core, where the black hole should be, silence, no strong X-ray source, no evidence of significant accretion. There were a few faint sources, but none with the characteristics expected from a supermassive black hole. The Chandra observations were crucial. They showed that if the black hole exists, it's remarkably quiet, not actively consuming gas in any significant way, or it's not there at all. The X-rays that revealed silence. The absence of X-rays is telling. In most galaxy clusters, the central galaxy's black hole is at least somewhat active, emitting enough X-rays to be detectable. The gas in galaxy clusters is hot and abundant, providing plenty of fuel for the black hole to feed on. So we'd expect to see X-ray emission. The fact that we don't suggests one of two things. Either the black hole is there but in an unusually dormant state, barely feeding despite the available gas, or the black hole isn't at the galaxy's center anymore. If it was ejected, it would have left behind the gas-rich environment, ending up in a region with little to no fuel. Without fuel, there's no accretion, no heating, no X-rays. The silence revealed by Chandra is a clue. It doesn't tell us definitively what happened, but it narrows the possibilities. A silent core in a gas-rich environment is unusual, and unusual things often have extraordinary explanation. The absence of energy in the core. Energy should be pouring out of the core. That's what happens in most massive galaxies. The central black hole feeds on gas, heats the surrounding material, and releases energy in the form of radiation and sometimes powerful jets. This energy regulates the galaxy and the cluster, preventing gas from cooling too quickly, influencing star formation. It's a crucial feedback mechanism. But in Abell 2261's central galaxy, this energy is absent. The core is cold, quiet, inactive. There's no sign of the feedback that black holes typically provide. This absence is puzzling. It suggests that whatever happened in this galaxy's past was dramatic enough to disrupt the normal cycle of black hole activity. Perhaps the black hole was ejected, removing the energy source. Or perhaps the galaxy's gas supply was disrupted, starving the black hole. Either way, the absence of energy in the core is another piece of the puzzle, another clue pointing toward an unusual history. The theories begin to form. With the observations in hand, astronomers began developing theories. What could explain the missing black hole and the strange core structure? One possibility is that the galaxy never had a very massive black hole to begin with. Perhaps its formation history was unusual, preventing a large black hole from forming, but this seems unlikely. The galaxy is too massive, too clearly formed through mergers. Another possibility is that the black hole is there, but simply undetectable with current instruments. Maybe it's dormant, surrounded by an unusually small amount of gas. But the most intriguing theory is the ejection hypothesis. If two supermassive black holes merged in the galaxy's past, the merger could have produced a gravitational wave recoil, powerful enough to kick the resulting black hole out of the core, or even out of the galaxy entirely. This theory, once considered exotic, suddenly had a potential example, and astronomers began exploring it in detail. The black hole that may have been ejected. Imagine two galaxies colliding. Their central black holes spiral toward each other, taking millions of years to merge. When they finally coalesce, the merger releases enormous energy in the form of gravitational waves. And if the two black holes weren't perfectly symmetric, if they had different masses or spins, the gravitational waves could be emitted preferentially in one direction. This creates a recoil, a kick, that pushes the merged black hole in the opposite direction. Most of the time, this kick is small, barely affecting the black hole's position. But in rare cases, if the conditions are just right, the kick can be enormous, powerful enough to eject the black hole from the galaxy's core, sending it flying through the outer regions, or even out of the galaxy entirely. This is what may have happened in Abell 2261, a catastrophic merger, an asymmetric recoil, and a black hole launched into the depths of space. The possibility of a gravitational kick, gravitational recoil, isn't just theoretical. It's been predicted by Einstein's general relativity and confirmed by observations of gravitational waves from merging black holes. When LIGO and other gravitational wave detectors observe black hole mergers, they can measure the recoil velocity. Most are modest, a few hundred kilometers per second, but simulations show that under the right conditions, recoils can reach several thousand kilometers per second, fast enough to escape a galaxy's gravitational pull. If Abell 2261's central galaxy experienced such a merger, the recoil could have ejected the black hole. This would explain the missing black hole, the large core, and the absence of central activity. The stars in the core would have responded to the black hole's departure, their orbits expanding, creating the diffuse structure we see. It's a dramatic scenario, almost violent in its implications. But it fits the observations remarkably well. The collision of two galactic giants, the ejection scenario, requires a major merger, not a small dwarf galaxy falling in, but two massive galaxies colliding, each with its own supermassive black hole. Such mergers are rare, but not unheard of. Galaxy clusters are dynamic places, and major collisions do happen, especially in their cores where galaxies are densest. If two large galaxies in Abell 2261 merged billions of years ago, their black holes would have spiraled together, eventually merging in a cataclysmic event. The galaxy that resulted from this merger would be the central giant we see today. And if the black hole merger produced a strong recoil, it could explain everything: the missing black hole, the strange core, the unusual structure. Evidence for past mergers can sometimes be found in the galaxy's structure, in shells or streams of stars, in disturbed gas distributions. Astronomers are searching for these signs, looking for confirmation that such a collision occurred. The recoil from merging black holes. When black holes merge, they don't just combine quietly. The merger is violent, releasing more energy in a fraction of a second than all the stars in the galaxy emit in a year. Most of that energy goes into gravitational waves, ripples in space-time that spread outward at the speed of light. But the emission isn't always symmetric. If the black holes have different masses or spins, the gravitational waves carry more momentum in one direction than the other. This creates a net recoil, pushing the merged black hole in the opposite direction. The magnitude of the recoil depends on the specifics of the merger, the mass ratio, the spins, their orientations. In the most extreme cases, the recoil can reach 5,000 kilometers per second or more. That's fast enough to escape most galaxies. For Abell 2261's central galaxy, even a recoil of 1,000–2,000 kilometers per second might be enough to displace the black hole significantly, moving it from the core to the outer regions, the lost heart of a galaxy. If the black hole was ejected, the galaxy lost its heart, the gravitational anchor that held the core together, that regulated the galaxy's evolution, that influenced star formation and gas dynamics. Gone. This would be an extraordinary event, with lasting consequences. The stars in the core would no longer orbit a central massive object. Their orbits would expand, creating the large, diffuse core we observe. The gas that would have fed the black hole would disperse or cool, unable to accrete onto anything, and the galaxy would lose the feedback mechanism that black holes provide, potentially changing how it evolves over time. A galaxy without its central black hole is rare, perhaps unprecedented. It's a cosmic oddity, a system missing its most massive component. And if that's what happened to Abell 2261's central galaxy, it makes this object one of the most unusual in the entire universe. The search for a wandering black hole. If the black hole was ejected, but didn't escape the galaxy entirely, it might still be out there, wandering through the outer regions. A 10 billion solar mass black hole moving through a galaxy would leave clues. It would gravitationally attract nearby stars, creating a concentrated group traveling through space together. This moving cluster of stars might be detectable with careful observations. Astronomers have searched the outer parts of the galaxy, looking for such concentrations. They've examined Hubble images, analyzed the motions of star clusters, searched for anomalies in the stellar distribution. So far, nothing definitive has been found, but the search continues. If the black hole is still in the galaxy, it's hiding well. Or perhaps it's already passed through the galaxy and escaped into intergalactic space, lost forever in the void between galaxies. Either possibility is extraordinary. The instruments turn to the void. Multiple instruments have joined the hunt for Abell 2261's missing black hole. Hubble has mapped the galaxy's structure in visible light. Chandra has searched for X-rays. Radio telescopes have looked for the signature of jets or accretion. Even gravitational wave observatories are indirectly involved, as their detections of black hole mergers and recoils inform the theoretical models. Each instrument provides a different perspective, a different wavelength, a different type of information, and together, they're building a comprehensive picture of the galaxy and its mystery. But so far, the black hole remains hidden. The void at the galaxy's core persists, unexplained and tantalizing. Astronomers are planning future observations with next-generation telescopes that might finally solve the mystery. But for now, the instruments have turned to the void and found only silence. The radio silence of the central region. Radio telescopes have also searched for the black hole. Many supermassive black holes emit radio waves, generated by jets of material launched from near the black hole at nearly the speed of light. These jets can extend for thousands or even millions of light years, making them visible across vast distances. If Abell 2261's black hole was active, even modestly so, it might emit detectable radio signals, but radio observations of the galaxy's central region have found nothing significant. No strong radio source, no jets, just the diffuse radio emission typical of galaxies, with many old stars and cosmic rays. The radio silence is consistent with the X-ray silence. Together, they paint a picture of a core that's remarkably quiet, lacking the activity we'd expect from a supermassive black hole. This silence is itself informative. It tells us that if the black hole is there, it's not actively feeding. And if it's not there, the silence makes sense. The pockets of cold gas surrounding the core. Interestingly, the galaxy does contain gas. Observations have detected pockets of cooler gas around the core, gas that could in principle feed a black hole if one were present. This gas is cold by astrophysical standards, just a few hundred or thousand degrees, cool enough to condense and potentially fall toward the center. In most massive galaxies, this gas would be pulled in by the central black hole's gravity, heated as it falls, and emit radiation. But here, the gas seems undisturbed. It's not falling toward a central point. It's not being heated by accretion. It simply sits there, scattered around the core region. This is another clue. If a massive black hole were at the center, it would be pulling this gas in, creating detectable activity. The fact that the gas remains undisturbed suggests that either the black hole isn't there, or it's in a location where it can't efficiently capture the gas. The traces of past mergers. The galaxy's structure holds evidence of its violent past. Astronomers have found subtle asymmetries in the stellar distribution, faint shells and streams that suggest past mergers. These features are common in elliptical galaxies, signatures of smaller galaxies that were torn apart and absorbed over time. In Abell 2261's central galaxy, these traces hint at a complex history of collisions. Each merger would have brought new stars, new gas, and potentially a new black hole to be absorbed into the growing giant. The large core itself is evidence of a major event, something that dramatically rearranged the stellar distribution. By studying these traces, astronomers can piece together the galaxy's history, identifying which mergers were most significant, estimating when they occurred, and understanding how they shaped the galaxy we see today. The past is written in the stars, waiting to be read. The star clusters that surround the center. Around the diffuse core, there are star clusters, globular clusters. Compact collections of old stars orbit the galaxy in wide paths. These clusters are fossils, formed billions of years ago, survivors of the galaxy's tumultuous history. By studying their properties, their ages, compositions, velocities, astronomers learn about the galaxy's evolution. Some clusters may have formed during the galaxy's initial assembly. Others might have been captured from smaller galaxies that merged with the central giant. The cluster's orbits are particularly informative. If a massive black hole were suddenly removed from the galaxy's center, the orbits of nearby clusters would change, expanding outward. By modeling the cluster's current orbits and working backward, astronomers can test whether the ejection hypothesis is consistent with the observed distribution. The star clusters are witnesses, their positions and motions preserving evidence of what happened billions of years ago. The size of the core, 10 times too large. The numbers are striking. Abell 2261's central galaxy has a core about 10,000 light-years across. Most elliptical galaxies of similar mass have cores of about 1,000 light-years or less. That's a factor of 10 difference, 10 times larger than expected. This discrepancy can't be explained by normal processes. Stars don't naturally spread out this much in a galaxy's core. Something had to push them there, to expand their orbits, to create this enormous hollow center. The leading explanation is the ejection of the central black hole. When the black hole departed, it took with it the gravitational glue holding the core together. The stars, no longer tightly bound, expanded outward, settling into new, larger orbits. Computer simulations support this scenario. When you model a black hole ejection, the core does expand, reaching sizes similar to what we observe in Abell 2261. The size of the core isn't just unusual, it's a fingerprint, evidence of a catastrophic event that reshaped the galaxy's center, the structure that defies galactic physics. Galaxy cores follow predictable patterns. There's a relationship between a galaxy's total mass and the size and density of its core. This relationship emerges from billions of years of evolution, from the interplay of gravity, star formation, and black hole growth. But Abell 2261's central galaxy doesn't fit the relationship. Its core is too large, too diffuse, completely inconsistent with standard models. This defiance of galactic physics is what makes the galaxy so important. It's an outlier, yes, but outliers are valuable. They push the boundaries of our understanding, forcing us to consider processes and events we might otherwise overlook. The structure of this galaxy tells us that something unusual happened here, something that normal galactic evolution can't explain. And by studying this structure, by understanding what created it, we learn about the extremes of cosmic processes, about the rare but important events that shape the universe. The stars that float in empty space. In the galaxy's core, stars orbit through what seems like empty space. There's no dense central concentration to anchor them. No massive black hole defining the gravitational center. They move on elongated orbits, some passing close to the center, others swinging far out before returning. It's an unusual configuration, almost eerie in its emptiness. These stars formed billions of years ago, when the galaxy was young. They've orbited the center for most of cosmic history, their paths shaped by whatever was there. If a black hole once occupied the center and was then ejected, these stars would have felt its departure. Their orbits would have changed, expanded, adjusted to the new gravitational landscape. By measuring the velocities of these stars, their orbital characteristics, astronomers can test different scenarios. They can determine whether the observed distribution is consistent with a past black hole ejection. The stars floating in empty space are clues, their motions encoding the history of dramatic events. The theory of a recoiling supermassive black hole. The recoiling black hole theory is elegant. It explains multiple observations with a single dramatic event. Two massive galaxies merge. Their central black holes spiral together and coalesce. The merger is asymmetric, producing a powerful gravitational wave recoil. The merged black hole is kicked, ejected from the core. The stars respond to its departure, their orbits expanding, creating the large diffuse core. And the black hole, now displaced, is either wandering through the outer galaxy or has escaped entirely, explaining why we can't detect it. This theory fits the observations remarkably well, but it's not proven. It remains a hypothesis, one of several possibilities. To confirm it, astronomers need more evidence. They need to find the ejected black hole, or at least find stronger signatures of the recoil event. They need to rule out alternative explanations. But for now, the recoiling black hole theory is the leading explanation for Abell 2261's mystery. The energy needed to launch it away. Ejecting a 10 billion solar mass black hole from a galaxy's core requires enormous energy. The gravitational binding energy is immense. To overcome it, the recoil velocity must be at least a few hundred kilometers per second, and preferably much more. Where does this energy come from? From the black hole merger itself. When two supermassive black holes merge, they convert a small fraction of their combined mass directly into gravitational wave energy. This might sound small, but with billions of solar masses involved, even a small fraction represents staggering amounts of energy. A typical supermassive black hole merger releases the equivalent of several solar masses worth of energy in gravitational waves. If this energy is emitted asymmetrically, it can produce the needed recoil. The physics is well understood, predicted by general relativity, and confirmed by gravitational wave observations. The energy is there. The question is whether the specific merger in Abell 2261 had the right conditions to produce a sufficiently strong kick. The distortion of space-time that could cause it. Gravitational waves are distortions in space-time itself, ripples that propagate outward from accelerating masses. When black holes merge, they create some of the most powerful gravitational waves in the universe. These waves carry momentum, and if the emission is asymmetric, if more waves are emitted in one direction than the opposite, the system experiences a net momentum transfer. This is the recoil. It's a direct consequence of space-time distortion, of the way mass and energy curve the fabric of the universe. The distortion is temporary, lasting only seconds during the final merger, but its effects are permanent. The merged black hole retains the velocity imparted by the recoil, moving through space with a speed determined by the asymmetry of the gravitational wave emission. It's a beautiful example of general relativity in action, of how the geometry of space-time influences the motion of objects, even objects as massive as supermassive black holes. The ripples of gravitational waves. The gravitational waves from the merger that may have occurred in Abell 2261 are long gone. They passed through our solar system over 2 billion years ago, before Earth even formed, propagating outward at the speed of light. We'll never detect those specific waves. They were spread too thin by the time they reached us. and we didn't have detectors back then anyway. But gravitational wave astronomy is now a reality. LIGO, Virgo, and other detectors are observing black hole mergers regularly, measuring their properties, including recoil velocities. These observations inform the theory, showing us what's possible, what recoil speeds are typical, and what are extreme, and they give us confidence that the recoiling black hole scenario for Abell 2261 is physically plausible. The ripples of gravitational waves connect the distant past of Abell 2261 to the present observations of merging black holes, linking distant mysteries to current discoveries. The Event Horizon Telescope joins the hunt. The Event Horizon Telescope, or EHT, is a global network of radio telescopes that can image the immediate vicinity of black holes with unprecedented resolution. The EHT famously imaged the black hole in the galaxy M87, showing the shadow of the event horizon, surrounded by glowing hot gas. Could the EHT find Abell 2261's missing black hole? In principle, yes. If the black hole is actively accreting gas, even modestly, the EHT might be able to detect and image it. But there's a challenge. Abell 2261 is very distant, over 2 billion light-years away. At that distance, even a supermassive black hole appears incredibly small, pushing the limits of what the EHT can resolve. Still, observations are being planned. If the black hole is there and active, the EHT might finally reveal it, providing direct confirmation and allowing astronomers to study its properties. The hunt continues, now with one of the most powerful instruments ever devised: the deepest search for a hidden black hole. The search for Abell 2261's black hole has been exhaustive. Astronomers have used nearly every available technique and instrument: optical observations to map the stellar distribution, X-ray observations to search for accretion signatures, radio observations to look for jets, gravitational wave data to understand what kinds of recoils are possible, computer simulations to model the galaxy's evolution and predict where an ejected black hole might be. Despite all this effort, the black hole remains hidden. It's a testament to how difficult it is to find a quiet black hole in a distant galaxy. Black holes don't emit light. They're visible only through their effects on surrounding material. If there's no material nearby, or if the black hole isn't actively feeding, it becomes nearly invisible. The deepest search has come up empty so far. But that doesn't mean it's over. New instruments, new techniques, and new observations may yet reveal the answer. The surprising lack of X-ray emissions. The lack of X-rays from the galaxy's core continues to surprise astronomers. Galaxy clusters are X-ray bright, their hot gas glowing across the spectrum, and the centers of massive galaxies, where gas is densest and black holes most active, are usually the brightest spots, but not in Abell 2261's central galaxy. The core is dark in X-rays. This darkness could mean the black hole is dormant, not feeding despite the available gas. Or it could mean the black hole isn't there at all. Both explanations are unusual. Supermassive black holes in gas-rich environments typically show at least some activity. The fact that this one doesn't is puzzling. Some astronomers have suggested that the gas might be too hot to accrete efficiently, staying in a stable configuration without falling in. But this seems unlikely given the conditions. The surprising lack of X-ray emissions remains one of the strongest pieces of evidence that something unusual has happened here. The possibility of a dormant black hole. Could the black hole simply be dormant? It's possible. Black holes don't always feed actively. If there's not enough gas in the immediate vicinity, or if the gas is too hot or moving too fast to accrete efficiently, the black hole can be quiet, emitting little to no detectable radiation. Some supermassive black holes go through cycles, alternating between active and quiescent phases, lasting millions of years. Abell 2261's black hole, if it exists, might be in a particularly deep quiescent phase, but even dormant black holes usually leave some signature. The motions of nearby stars should reveal the black hole's gravitational influence. Yet in this galaxy, even that signature is unclear. The stellar velocities don't show the sharp increase toward the center that would indicate a concentrated massive object. So while dormancy is possible, it doesn't fully explain the observations. The mystery remains. The cold silence at the heart of a giant. There's something haunting about the silence at the galaxy's heart. In most massive galaxies, the center is active, dynamic, filled with energy. Gas swirls into the black hole. Stars orbit at tremendous speeds. Jets erupt, carrying energy outward. But here, there's cold silence. No dramatic activity. No clear central anchor. Just stars moving through space, gas sitting undisturbed, and a vast empty core where something should be. This silence is the most striking feature of Abell 2261's central galaxy. It's a negative observation, the absence of something expected, and sometimes absences are more informative than presences. The cold silence tells us that whatever happened here was dramatic enough to fundamentally alter the galaxy's core, to remove or silence the engine that should be driving its evolution. It's a cosmic crime scene, and the silence is the loudest clue, the puzzling age of its stellar population. The stars in the galaxy's core are old, but not uniformly so. Astronomers have measured their ages and found a spread, suggesting multiple generations of star formation over billions of years. This isn't unusual in itself. Most massive galaxies have complex star formation histories, but what is puzzling is the lack of very recent star formation in the core. Normally, gas falling toward the center can trigger bursts of star formation, especially after major mergers. Yet the core appears to have been quiescent for a long time, with little recent star formation. This could be because the black hole, if it was ejected, took with it the gravitational focus that would have funneled gas toward the center. Or it could be because the merger that created the large core also disrupted the gas supply, preventing new stars from forming. The puzzling age distribution is another piece of the puzzle, another clue about the galaxy's unusual history. The history of collisions in the cluster. Abell 2261 itself has a violent history. Galaxy clusters grow through mergers, smaller groups falling in and combining over billions of years. Abell 2261 is no exception. There's evidence of past collisions in the distribution of galaxies, in the properties of the hot gas, in the overall structure of the cluster. Some of these collisions were minor, small groups merging with the main cluster. Others were major, comparable mass clusters colliding in spectacular encounters. These collisions stir up the cluster, redistribute the gas, trigger star formation, and can even affect the central galaxies. The merger that may have ejected Abell 2261's central black hole was probably part of this larger history of collisions. Two massive galaxies in the cluster core collided, their black holes merged, and the recoil kicked one of them out. The cluster's violent history sets the stage for the galaxy's unusual structure. The motion of galaxies within the web. Within Abell 2261, galaxies are in constant motion. They orbit the cluster's center, following paths dictated by the combined gravity of all the mass in the cluster. Some galaxies move quickly, whipping around the core in elongated orbits. Others move more slowly, drifting through the cluster's outskirts. And occasionally, galaxies collide, their paths intersecting, leading to mergers that reshape both participants. These motions are complex, influenced by the cluster's total mass, its distribution, and the individual interactions between galaxies. By measuring the velocities of many galaxies, astronomers can map the cluster's gravitational field, revealing the distribution of both visible and dark matter. The motion of galaxies within the web is a record of the cluster's dynamics, a snapshot of the gravitational dance that's been ongoing for billions of years. The gravitational pull binding them all. What holds a galaxy cluster together? Gravity. The combined gravitational pull of hundreds of galaxies, trillions of stars, vast clouds of hot gas, and enormous amounts of dark matter. This gravity is immense, creating a deep gravitational well that keeps galaxies bound to the cluster, despite their high velocities. Without this pull, the cluster would disperse, galaxies flying apart into the cosmic void. But with it, the cluster persists, a stable structure lasting for billions of years. In Abell 2261, the gravitational pull is particularly strong because the cluster is so massive. It's one of the most massive clusters known, containing as much mass as several thousand Milky Way galaxies. This gravity shapes everything: the motion of galaxies, the distribution of gas, the evolution of the central galaxy. It's the invisible hand that binds them all together, maintaining order in what would otherwise be chaos. The hot gas that fills the cluster. Between the galaxies of Abell 2261, there's gas, lots of it, hot plasma, heated to tens of millions of degrees, filling the space between galaxies like an atmosphere. This gas contains more mass than all the stars and all the galaxies combined. It's the largest reservoir of normal matter in the cluster. The gas is hot because of the cluster's gravitational energy. As the cluster formed, gas fell into the gravitational well, gaining energy, heating up, and it stays hot, maintained by the ongoing gravitational interactions and occasional shocks from merging subgroups. This hot gas is visible in X-rays, glowing brightly across the cluster. By studying its properties, temperature, density, chemical composition, astronomers learn about the cluster's history, its mass, and the processes shaping its evolution. The hot gas that fills the cluster is a key component, influencing everything from galaxy evolution to the search for the missing black hole. The glow of X-rays across light years. The X-ray glow of Abell 2261 extends for millions of light years, a vast halo of hot plasma surrounding the cluster's galaxies. This glow is beautiful in false color images, showing the distribution of gas in shades of blue and purple. But it's more than just pretty. It's informative. The X-ray emission traces the gas density and temperature, revealing the cluster's structure. Bright regions indicate dense, hot gas, often found near the cluster core. Dimmer regions show where the gas is cooler or more diffuse. And by mapping the X-ray glow in detail, astronomers can identify substructures, regions where smaller groups have recently merged, creating shocks and disturbances in the gas. The Chandra X-ray Observatory has mapped Abell 2261's glow extensively, searching for clues about the missing black hole, studying the cluster's evolution, and revealing the complex interplay between gas and gravity across light years of space. The evidence of dark matter in motion. Dark matter doesn't emit light, but it does have gravity, and that gravity affects everything around it. In Abell 2261, dark matter dominates the mass budget, outweighing the visible stars and gas by a factor of 5 or more. This dark matter forms a vast halo, extending far beyond the cluster's visible extent. By studying the motion of galaxies, astronomers can infer the distribution of dark matter. Fast-moving galaxies near the cluster's edge indicate a deep gravitational well, evidence of substantial dark matter mass. Similarly, the hot gas is held in place by dark matter's gravity. If the dark matter weren't there, the gas would evaporate, dispersing into the surrounding space. The evidence of dark matter in motion is everywhere in Abell 2261, from galaxy velocities to gas distributions to gravitational lensing. It's a reminder that most of the universe's mass is invisible, detectable only through its gravitational effects. The mapping of invisible mass. Mapping dark matter is challenging because it doesn't emit or absorb light, but it's possible through indirect methods. One technique is to measure galaxy velocities and use them to infer the gravitational potential. Another is to study gravitational lensing, the bending of light by the cluster's gravity. By combining these methods, astronomers can create maps of the cluster's total mass distribution, including the invisible dark matter. For Abell 2261, such maps reveal a concentrated core of dark matter, with density decreasing toward the edges. The dark matter halo extends far beyond the visible cluster, perhaps spanning tens of millions of light-years. This invisible mass is the foundation upon which the cluster is built. Without it, Abell 2261 wouldn't exist. The mapping of invisible mass is one of astronomy's great achievements, revealing a hidden component of the universe that shapes everything we see, the cosmic web that holds it together. Abell 2261 isn't isolated. It's part of a larger structure, the cosmic web. This web is the universe's large-scale architecture, a network of filaments, sheets, and nodes that spans billions of light-years. Galaxy clusters like Abell 2261 sit at the nodes, the intersections where filaments meet. Along these filaments, galaxies and gas flow, funneled toward the clusters by gravity. The cosmic web is made primarily of dark matter, with visible matter tracing its structure. By studying clusters like Abell 2261, astronomers learn about the web's properties, how it formed, how it's evolving. The web holds everything together, connecting distant structures through gravity's invisible threads. Abell 2261 is a node in this web, a hub where matter accumulates, where galaxies cluster, where cosmic evolution plays out at its grandest scales. The lensing effect of gravity. Massive objects bend light. This is gravitational lensing, a prediction of Einstein's general relativity, and a powerful astronomical tool. Abell 2261, with its enormous mass, acts as a gravitational lens, bending and magnifying the light of more distant galaxies behind it. This lensing effect is visible in deep images, where background galaxies appear distorted, stretched into arcs and multiple images. By studying these distortions, astronomers can map the cluster's mass distribution with exquisite precision. The lensing reveals not just the visible matter, but the dark matter too, showing where the gravitational field is strongest. For Abell 2261, lensing studies have confirmed that it's an extremely massive cluster with a deep gravitational potential. The lensing effect of gravity transforms the cluster into a natural telescope, allowing us to study both the cluster itself and the distant universe beyond it. The warping of background galaxies. In images of Abell 2261, you can see them, background galaxies, far beyond the cluster, their light warped and stretched by the cluster's gravity. Some appear as long, thin arcs, wrapped around the cluster core. Others are split into multiple images, the same galaxy visible in several locations. These distortions are beautiful and informative. Each one is a direct measurement of the cluster's gravitational field, a tracer of the mass distribution. By analyzing the shapes and positions of these lensed galaxies, astronomers can reconstruct the cluster's mass profile, distinguishing between different models of dark matter distribution. The warping of background galaxies is a gift from general relativity, a way to weigh the cluster using light from distant sources, and in the process, astronomers learn not just about Abell 2261, but about the nature of gravity itself. The clues hidden in bent light. Every lensed galaxy is a clue. The degree of distortion reveals the strength of the gravitational field. The position of the images constrains the mass distribution, and by combining data from many lensed galaxies, astronomers build a detailed picture of the cluster's structure. For Abell 2261, lensing studies have shown that the cluster's mass is concentrated toward the center, consistent with a massive dark matter halo. But lensing can also reveal substructures, smaller concentrations of mass within the cluster, evidence of past or ongoing mergers. The clues hidden in bent light are subtle, requiring careful analysis and sophisticated modeling, but they're invaluable. They allow astronomers to see the invisible, to map the dark matter that dominates the cluster's mass, and to test fundamental theories of gravity and cosmology. The bent light around Abell 2261 is more than a pretty effect. It's a window into the cluster's hidden structure. The study of Abell 2261 as a gravitational lens. Abell 2261 has been studied extensively as a gravitational lens. Deep imaging campaigns with Hubble and ground-based telescopes have identified dozens of lensed galaxies, their distorted shapes mapped in exquisite detail. These observations have been used to create mass models, reconstructing the three-dimensional distribution of matter in the cluster. The results confirm that Abell 2261 is exceptionally massive, with a total mass of several thousand trillion solar masses, most of it in dark matter. The lensing studies also reveal the cluster's overall shape, slightly elongated rather than perfectly spherical, suggesting it's still dynamically active, perhaps still accreting material. As a gravitational lens, Abell 2261 is a natural laboratory for testing general relativity, for studying dark matter, and for magnifying distant galaxies that would otherwise be too faint to see. It's a tool and a subject of study, offering insights into both its own nature and the universe beyond. The windows into the early universe, the lensed galaxies behind Abell 2261, are some of the most distant objects we can study. These galaxies existed when the universe was younger, their light traveling billions of years to reach us. By studying them, astronomers learn about the early universe, about how galaxies formed and evolved in cosmic history. Abell 2261's gravitational lensing magnifies these distant galaxies, making them brighter and easier to study. Without the lensing, many would be too faint for even our best telescopes to detect. The cluster acts as a natural telescope, a gift from nature that allows us to peer back in time. The windows into the early universe, opened by Abell 2261's lensing, are invaluable for cosmology, for understanding galaxy evolution, and for studying the conditions that existed billions of years ago, when the universe was young and very different from today. The light of distant galaxies seen through it. Through Abell 2261, we see light from galaxies that existed when the universe was less than half its current age. These galaxies are forming stars rapidly, building up their mass, evolving into the mature galaxies we see in the nearby universe. Their light, stretched and magnified by the cluster's gravity, reveals details about star formation, chemical composition, and structure that would be invisible without the lensing boost. Some of these distant galaxies are among the first being studied by the James Webb Space Telescope, which can see them in infrared light, penetrating the dust that obscures visible observations. The light of distant galaxies, seen through Abell 2261, is a treasure trove of information, connecting the early universe to the present, showing us the cosmic journey from simple proto-galaxies to the complex structures we see today. The history written in its structure. Abell 2261 structure is a history book. Every feature, every asymmetry, every unusual characteristic tells part of the story. The large, diffuse core of the central galaxy speaks of a dramatic past event. The distribution of hot gas reveals past mergers and shocks. The positions and velocities of member galaxies trace the cluster's assembly history, and the presence of lensed background galaxies constrains the mass distribution, showing how dark matter is arranged. By reading this structure carefully, astronomers piece together the cluster's history, reconstructing the sequence of mergers and collisions that built it over billions of years. The history written in its structure is incomplete. Some details are lost, eroded by time and subsequent events, but enough remains to paint a broad picture of violent assembly, of countless galaxies falling into the growing cluster, of major mergers that reshaped the core, and perhaps of a black hole ejection that left the central galaxy forever changed. The remnants of ancient collisions. Ancient collisions leave traces. In Abell 2261, These traces appear as faint shells in streams of stars, disturbances in the hot gas distribution, and asymmetries in the overall structure. Each collision, whether between galaxies or between subclusters, injects energy into the system, stirring things up, creating features that persist for billions of years. Astronomers search for these remnants, using them to identify past mergers and understand the cluster's growth history. The central galaxy itself is likely a remnant, formed from the collision of multiple smaller galaxies over time. And the large core might be a remnant of a particularly significant collision, one that involved the merger of two supermassive black holes and resulted in a recoil powerful enough to eject one. The remnants of ancient collisions are everywhere in Abell 2261, subtle but readable to those who know how to look. The clouds of intergalactic gas. Beyond the hot X-ray emitting plasma, there are cooler clouds of intergalactic gas scattered throughout Abell 2261. These clouds are at lower temperatures, just thousands of degrees rather than millions, and they emit light at different wavelengths. Some can be detected through their absorption of background light, creating dark lines in the spectra of distant quasars. Others emit faint optical or ultraviolet light. These clouds are remnants of past galaxy interactions, gas stripped from galaxies as they move through the cluster, or gas that never condensed into galaxies in the first place. They're important because they represent a reservoir of material that could potentially fuel star formation or feed black holes. In Abell 2261's central galaxy, the presence of cooler gas around the core might have provided fuel for the central black hole, if it were still there. The clouds of intergalactic gas are part of the cluster's ecosystem, connecting the galaxies to their environment. The temperature of the cluster's core. The temperature of the gas in Abell 2261's core is about 10 million degrees Celsius. This extreme heat is generated by the gravitational energy of the cluster. As gas falls into the cluster's deep gravitational well, it heats up, converting potential energy into thermal energy. The temperature is high enough that the gas is fully ionized, a plasma where electrons are stripped from atoms, and it emits strongly in X-rays. By measuring the temperature and density of this gas, astronomers can estimate the cluster's total mass, including dark matter. The temperature also reveals information about the cluster's dynamical state. A relaxed cluster has a smooth temperature distribution, while a disturbed cluster shows temperature variations and shocks from ongoing mergers. Abell 2261's core temperature is fairly uniform, suggesting the cluster is relatively relaxed now. Though its history was clearly violent, the temperature of the cluster's core is a diagnostic, a thermometer measuring the cluster's gravitational energy. The cooling flows and star formation. In some galaxy clusters, the hot gas in the core cools over time, losing energy to radiation. This cooling gas can then condense, forming clouds that collapse to form new stars. Astronomers call this process a cooling flow, and it was once thought to be common in massive clusters. But observations revealed that cooling flows don't produce as many stars as expected. Something is heating the gas, preventing it from cooling too much. In most clusters, that something is the central black hole, which injects energy through jets and radiation. But in Abell 2261, the apparent absence of an active black hole raises questions. Is the gas cooling? Is star formation happening in the core? Current observations suggest that star formation is minimal, despite the presence of cooler gas. This could be because the gas hasn't had time to cool and collapse, or because some other heating mechanism is at work. The calm between cosmic storms. Right now, Abell 2261 appears relatively calm. There's no major merger ongoing, no dramatic disturbance in the gas distribution. The cluster is in a relaxed state, having settled after past collisions. But this calm is temporary. In the universe, galaxy clusters are always evolving, always subject to new perturbations. Smaller groups may be falling into Abell 2261, even now. their arrival yet to cause significant disruption. And in the distant future, the cluster may merge with neighboring clusters, triggering new waves of star formation, new disturbances in the gas, new chapters in its ongoing story. The calm between cosmic storms is a brief respite, a moment of relative peace in an otherwise violent history. It's a chance for astronomers to study the cluster in detail, to understand its current state before the next storm arrives. And it's a reminder that in the cosmos, nothing stays still for long. The expansion of the universe and its effect. While Abell 2261 is gravitationally bound, held together by its own mass, the space around it is expanding. The universe itself is growing larger, driven by dark energy, a mysterious force that counteracts gravity on the largest scales. This expansion affects how we see the cluster. Its light is redshifted, stretched to longer wavelengths as space expands during the light's journey to us. And it means that distant clusters are receding from us, carried away by the expansion. But within the cluster, expansion is negligible. Gravity wins, holding the galaxies together. The expansion of the universe and its effect on Abell 2261 is subtle. It shifts the cluster's light, making it appear redder, and it places the cluster in the context of cosmic evolution. The cluster formed when the universe was younger, denser, more conducive to structure formation. And as the universe continues to expand, such massive clusters may become rarer, more difficult to form in the increasingly diffuse cosmos. The redshift that reveals its distance. The Abell 2261 has a redshift of about 0.224. That number, measured from the spectrum of its galaxies, tells us how much the universe has expanded since the light left the cluster. The redshift of 0.224 means the universe is about 1.224 times larger now than it was when the light began its journey. This translates to a distance of over 2 billion light-years and a look-back time of about 2 billion years. The redshift is a fundamental measurement, connecting the cluster to cosmic history. It places Abell 2261 in the relatively recent past, cosmically speaking, when the universe was about 80% of its current age. The redshift that reveals its distance also tells us about the cluster's motion, its place in the expanding universe, and the era in which we're seeing it. It's a single number that encodes vast amounts of information about distance, time, and cosmic evolution. The age of the light we see. The light we see from Abell 2261 is about 2 billion years old. It left the cluster long before humans existed, before complex life evolved on Earth. This light has been traveling through space all that time, crossing vast cosmic voids, passing through the expanding universe, finally reaching our telescopes today. In those 2 billion years, the cluster has continued to evolve. Stars have been born and died. Galaxies have merged. The structure has changed, but we don't see any of that. We see only the light that left 2 billion years ago, a snapshot of the cluster, frozen in the past. The age of the light we see is a reminder that astronomy is fundamentally a study of history. Every observation looks back in time, and distant objects, like Abell 2261, offer windows into the universe as it was, not as it is now. The state of the universe. When it began. When Abell 2261 formed, the universe was different, denser, younger. Star formation rates across the universe were higher. Galaxy mergers were more common. The cosmic microwave background was slightly warmer, and dark energy, though always present, was less dominant than it is today. The cluster formed through the collapse of an overdense region, a place where dark matter and gas were slightly more concentrated than average. Over time, this region grew, pulling in more material, building up the massive structure we see today. Understanding the state of the universe, when Abell 2261 began, helps astronomers place the cluster in context, understanding not just its own evolution, but its role in the larger story of cosmic structure formation. The cluster is a product of its time, shaped by the conditions of the universe, billions of years ago. The role of Abell clusters in cosmic mapping. Abell clusters, like Abell 2261, are landmarks in cosmic mapping. They're among the largest structures in the universe, visible across billions of light years, and they trace the cosmic web's nodes. By cataloging and studying these clusters, astronomers map the large-scale structure of the universe, revealing the distribution of matter, the influence of dark energy, and the history of cosmic expansion. Abell's original catalog was a pioneering effort, and modern surveys have built upon it, identifying thousands of additional clusters. Each one is a data point, a measurement of where matter has accumulated, how the universe is structured. Abell 2261's role in cosmic mapping is both specific. It's a massive cluster at a specific location, and general. It represents a class of objects that define cosmic structure. By studying it and clusters like it, astronomers piece together the universe's architecture. The studies that define cosmic evolution. Studies of Abell 2261. Similar clusters are fundamental to understanding cosmic evolution. How do structures grow from tiny density fluctuations in the early universe to the massive clusters we see today? How do galaxies evolve within clusters? What role do black holes play in regulating galaxy growth? These questions can only be answered by studying clusters across cosmic time, comparing their properties at different epochs. Abell 2261, with its unusual central galaxy and missing black hole, offers a unique window into extreme processes. It's not just another cluster, it's an outlier, a place where something extraordinary happened, and by understanding what that was, astronomers refine their models of galaxy and black hole evolution. The studies that define cosmic evolution rely on both typical examples and exceptional ones. Abell 2261 is exceptional, and its mystery, once solved, will contribute to the broader understanding of how the universe came to be the way it is. The scale of time in astronomical terms, 2 billion years. It's a number so large it loses meaning. To put it in perspective, 2 billion years ago on Earth, life was single-celled. The first complex organisms wouldn't appear for another billion years. The continents were arranged differently. The planet was unrecognizable compared to today. And during all that time, light from Abell 2261 has been traveling toward us. In astronomical terms, 2 billion years is relatively recent. The universe is nearly 14 billion years old, so we're seeing Abell 2261 when the cosmos was already mature, about 85% of its current age. But in human terms, it's incomprehensible. The scale of time in astronomical terms forces us to think differently, to consider processes that unfold over billions of years, changes so slow they're imperceptible, except when viewed across cosmic history. Abell 2261's story plays out on this timescale, a saga spanning eons, the billions of years since its formation. Abell 2261 has existed for billions of years, perhaps forming when the universe was only a few billion years old. Since then, it's grown through accretion and mergers, accumulating galaxies, gas, and dark matter. The central galaxy formed early, through the merger of several large galaxies, and has been growing ever since, consuming smaller neighbors. The cluster's hot gas accumulated gradually, heated by infalling material and gravitational energy. And throughout this time, the cluster has been evolving, its structure shaped by countless interactions and collisions. The billions of years since its formation have seen dramatic changes, from the initial assembly to the mature cluster we observe today. But they've also seen long periods of relative quiet, when evolution proceeded slowly, gradually, without major upheavals. Understanding this timescale helps astronomers appreciate how structures like Abell 2261 came to be, and how they'll continue to evolve in the future. The fusion of smaller groups into one. Abell 2261 didn't form in a single event. It's the result of countless smaller groups and individual galaxies falling together over billions of years. Each group brought its own galaxies, its own hot gas, its own dark matter. When they merged with the growing cluster, their material was incorporated, adding to the cluster's mass. Some mergers were minor, barely noticeable. Others were major, comparable masses colliding, creating shocks in the gas, triggering star formation in the galaxies. This hierarchical assembly is the standard model for how cosmic structures form. Small things merge to make bigger things, and bigger things merge to make even bigger things. Abell 2261 is the product of this process, a fusion of smaller groups into one massive cluster, and the process continues. The cluster is still accreting material, still growing, still evolving through the ongoing fusion of smaller structures into the whole. The growth of structure across time. Cosmic structure grows over time, from tiny quantum fluctuations in the early universe to the vast clusters we see today. In the beginning, just after the Big Bang, the universe was nearly uniform, with only tiny density variations. But these variations, amplified by gravity over billions of years, grew into the structures we observe. First, small clumps of dark matter formed. Then, gas fell into these clumps, forming the first stars and galaxies. Galaxies clustered together, forming groups. Groups merged into clusters, and clusters connected along filaments, forming the cosmic web. Abell 2261 represents a stage in this growth, a massive cluster that's assembled over billions of years and continues to grow. The growth of structure across time is one of cosmology's grand narratives, the story of how gravity shaped the universe, turning smooth beginnings into the complex structured cosmos we inhabit today. The gravity that rules all in the cluster. In Abell 2261, gravity is the dominant force. It determines the motion of galaxies, the distribution of gas, the paths of light rays passing through. Gravity holds the cluster together, despite the enormous kinetic energy of its members. And gravity drives the cluster's evolution, pulling in new material, causing mergers, heating the gas. Every process in the cluster is ultimately governed by gravity. The missing black hole mystery is fundamentally a gravitational question. If the black hole was ejected, it was gravity, in the form of gravitational wave recoil, that did it. If the black hole is displaced, but still in the galaxy, gravity determines where it is and how it moves. And if future observations finally locate it, gravity will have been the key to solving the mystery. The gravity that rules all in the cluster is both the force that creates order and the force that can create chaos, depending on the circumstances. The ongoing mergers still happening today. Abell 2261's evolution isn't over. Right now, as you read this, mergers are probably happening within the cluster. Smaller galaxies are falling into larger ones, their stars and gas being absorbed. Subgroups may be merging with the main cluster, adding their mass and energy. These processes are slow by human standards, taking millions of years to complete, but they're ongoing. The cluster is a dynamic system, constantly changing, constantly evolving. In a billion years, Abell 2261 will look different. Some galaxies will have merged, new stars will have formed, old stars will have died, the hot gas distribution will have changed, and perhaps new observations in that distant future will reveal more about the missing black hole, whether it's been found or remains hidden. The ongoing mergers happening today are part of the cluster's continuous story, chapters still being written in the cosmic narrative. The faint glows of distant members. Around the edges of Abell 2261, faint galaxies glow dimly. These are distant members, orbiting far from the cluster core, weakly bound by gravity. Some are dwarf galaxies, small collections of stars barely massive enough to be called galaxies. Others are more substantial, but simply far away, their light dimmed by distance. These distant members are important. They trace the cluster's gravitational influence, showing how far its reach extends. They're also potential future meals for the central galaxy. Over billions of years, some will spiral inward, eventually merging with the core. Others will remain in the outskirts, orbiting endlessly, never falling in. The faint glows of distant members remind us that clusters aren't neat, compact objects. They're extended, diffuse, with fuzzy boundaries that gradually transition from clustered structure to the general cosmic background. Abell 2261's influence extends far beyond what's immediately visible. The star formation that once burned bright billions of years ago. Star formation in Abell 2261's galaxies was vigorous. Gas was abundant. Galaxies were younger, and mergers triggered bursts of star formation that lit up the cluster with blue light. The central galaxy, still assembling from smaller pieces, was likely a starburst galaxy, forming new stars at prodigious rates. But over time, star formation has declined. The galaxies have aged. Much of their gas has been consumed, forming stars that now populate the galaxies. And interactions with the hot cluster gas have stripped remaining gas from many galaxies, quenching their star formation entirely. The star formation that once burned bright is now reduced to a flicker. Some galaxies still form stars, particularly those recently fallen into the cluster, but most are quiescent, dominated by old red stars. This decline in star formation is typical of massive clusters, where environmental effects suppress the processes that create new stars. The aging of the galaxies within. The galaxies in Abell 2261 are aging. Their stellar populations are getting older, redder, dimmer. Massive blue stars, which burn brightly but briefly, have long since died, leaving behind only their longer-lived, less massive companions. These surviving stars are red giants and red dwarfs, stars in the later stages of their lives, or stars so small they'll burn for trillions of years. As the galaxies age, their overall color shifts from blue to red, a visual indication of their stellar population's maturity. This aging is particularly pronounced in the central galaxy and other massive ellipticals, which stopped forming stars billions of years ago. In spiral galaxies, if any remain, star formation may continue in the outskirts, but even there, it's slowing. The aging of the galaxies within Abell 2261 is a natural consequence of time and environment, a progression toward cosmic old age, the cooling of stars into red giants. As stars age, they evolve, sun-like stars, after billions of years of steady fusion, begin to run out of hydrogen in their cores. They respond by expanding, swelling into red giants, stars hundreds of times larger than their original size. In Abell 2261's older galaxies, many stars are in this phase, glowing red and cool, having left their main sequence youth behind. These red giants dominate the light of elliptical galaxies, giving them their characteristic golden red color. Eventually, these red giants will shed their outer layers, leaving behind white dwarf cores, slowly cooling stellar remnants. The cooling of stars into red giants is a phase of stellar evolution, a natural aging process, and in a cluster as old as Abell 2261, where many stars formed billions of years ago, red giants are common, a visible reminder that even stars have life cycles, growing old and fading like everything else. The dimming of light across the eons. Over cosmic time, Abell 2261 is dimming. As stars age and die, they're not replaced at the same rate. Star formation has slowed dramatically, so fewer new stars are being born to replace the old ones that fade. The massive blue stars that once lit the cluster brightly are gone, replaced by dimmer red stars and stellar remnants. Over billions of years, this process will continue. The cluster will grow redder and dimmer, its total light output declining. Eventually, In the far future, the cluster will be a graveyard of dead and dying stars, glowing faintly in the darkness. But that's trillions of years away. For now, Abell 2261 still shines, still glows with the light of billions of stars, still bright enough to study from across the universe. The dimming of light across the eons is slow, almost imperceptible, but inevitable. Everything fades, given enough time. The black holes that remain after the stars die. When massive stars die, they leave behind black holes, stellar mass black holes, typically 10 to a few dozen times the sun's mass, scattered throughout the galaxies of Abell 2261. These black holes are invisible, emitting no light, but they're there, dark remnants of stars that once burned bright. In the cluster as a whole, there may be millions of these stellar mass black holes, quietly orbiting within their host galaxies. Occasionally, one might accrete gas from a companion star, flaring up as an X-ray binary, but most remain silent, invisible, detectable only through their gravitational effects. These stellar mass black holes are different from the supermassive black hole at the galaxy's center, or the one that's missing, but they're part of the same continuum. Objects where gravity has become so strong that nothing, not even light, can escape. The black holes that remain after the stars die are the universe's most enigmatic objects, windows into the extremes of physics, the web of dark matter beneath the cluster. Beneath everything we can see in Abell 2261, there's the dark matter web, an invisible scaffolding, a structure of dark matter that holds the cluster together, that provides the gravitational foundation upon which everything else is built. This web extends far beyond the visible cluster, connecting Abell 2261 to neighboring structures along filaments stretching across millions of light years. The web is dense at the cluster's center, where dark matter is concentrated, and thinner at the edges, gradually transitioning to the cosmic background. Without this web, Abell 2261 wouldn't exist. The galaxies would disperse, the hot gas would evaporate, the structure would dissolve. But with the web, everything holds together, bound by dark matter's invisible gravity. The web of dark matter beneath the cluster is the foundation, the skeleton, the essential structure that makes everything else possible. And yet, we still don't know what dark matter actually is. The unseen hand that shapes the cosmos. Dark matter is the unseen hand that shapes the cosmos. It guided the formation of the first structures. After the Big Bang, it pulled galaxies together into clusters. It carved the cosmic web, and it continues to influence everything, from the motion of galaxies to the bending of light. In Abell 2261, dark matter's influence is everywhere. It's in the high velocities of galaxies, velocities that would be impossible without substantial invisible mass. It's in the gravitational lensing, the bending of background galaxy light, that reveals the cluster's true mass. It's in the distribution of hot gas, held in place by dark matter's gravity. The unseen hand shapes everything, working silently, invisibly, but powerfully. Understanding dark matter is one of physics' greatest challenges, and clusters like Abell 2261, where dark matter's effects are so pronounced, are crucial laboratories for studying this mysterious substance. The clues about how galaxies evolve. Abell 2261 offers clues about how galaxies evolve, particularly in dense environments. Galaxies and clusters behave differently than isolated galaxies. They interact more frequently, merging and colliding. They can be stripped of their gas by ram pressure as they move through the hot cluster medium, and they're influenced by the cluster's overall gravitational field. The central galaxy of Abell 2261, with its unusual structure, shows what can happen in the most extreme cases. Most galaxies don't have their black holes ejected, but the processes that led to this galaxy's structure, mergers, black hole growth, dynamical interactions, are universal. By studying Abell 2261, astronomers learn about these processes in their most extreme manifestation, and those lessons apply to galaxies everywhere, in clusters and in the field, helping build a comprehensive picture of how galaxies form, grow, and evolve over cosmic time. The questions that still remain, despite years of study, questions remain. Where is the black hole? Was it truly ejected? Or is it hiding somewhere in the galaxy, too quiet to detect? If it was ejected, how fast was it moving? Did it escape the galaxy entirely? Or is it wandering through the outer regions? And if we can't find it, what does that tell us about the limits of our instruments and techniques? Beyond the black hole question, there are broader mysteries. How common are such ejections? Could there be other galaxies with missing black holes yet to be discovered? What does this tell us about black hole mergers and gravitational wave recoils? The questions that still remain drive ongoing research. They motivate new observations, new theoretical work, new simulations. Abell 2261's mystery isn't just a puzzle to solve. It's a doorway to deeper understanding, to new questions, to new discoveries about the universe's most extreme phenomena. The search for the missing core continues. The search isn't over. Astronomers continue to study Abell 2261, applying new techniques, using new instruments, analyzing old data with fresh eyes. Every year, telescopes become more sensitive, analysis methods improve, and the possibility remains that the black hole will be found, that some observation will finally reveal its location and properties. The search for the missing core continues because the question matters. It's not just about one black hole in one galaxy. It's about understanding fundamental processes, testing theories of gravity and black hole dynamics, pushing the boundaries of what we know. And even if the black hole is never found, the search itself is valuable. It teaches us about the limits of detection, about how black holes can hide, about the diverse ways galaxies can evolve. The search continues, driven by curiosity, by the human need to understand, by the conviction that the answer is out there, waiting to be discovered. The new telescopes that will join the hunt. New telescopes are coming online, and they'll join the hunt for Abell 2261's missing black hole. Ground-based observatories, with adaptive optics, can image the galaxy with incredible resolution. Space-based X-ray telescopes, more sensitive than Chandra, will search for faint accretion signatures, and radio interferometers, with unprecedented resolution, will look for jets or other signs of black hole activity. Each new instrument brings new capabilities, new sensitivities, new ways of looking at the problem. The hope is that one of these new telescopes will finally spot the black hole, revealing what's been hidden for so long. The new telescopes that will join the hunt represent the cutting edge of astronomical technology, instruments designed to push beyond current limits, to see what's never been seen before. And Abell 2261 will be a prime target, a test case for these new capabilities. The promise of James Webb observations. The James Webb Space Telescope has already begun to revolutionize astronomy, and it holds promise for Abell 2261 too. Webb's infrared vision can penetrate dust, revealing hidden structures in the galaxy's core. Its sensitivity allows it to detect faint objects that other telescopes miss, and its spectroscopic capabilities can analyze the properties of stars and gas with unprecedented precision. Webb could potentially detect a displaced black hole by identifying a moving concentration of stars, or by finding infrared signatures of accretion that X-ray telescopes can't see. Observations are being planned, proposals written. The promise of James Webb observations is that they might finally solve the mystery, providing the missing piece of the puzzle, or they might deepen the mystery, revealing new complexities we haven't anticipated. Either way, Webb's contribution to understanding Abell 2261 will be significant. The future of gravitational wave astronomy. Gravitational wave astronomy is still in its infancy, but it's rapidly maturing. Current detectors like LIGO and Virgo observe stellar mass black hole mergers. Future detectors, like the space-based LISA mission, will observe supermassive black hole mergers, the kind that may have occurred in Abell 2261 billions of years ago. These future observations won't detect the specific merger in Abell 2261. That event is long past, its gravitational waves long dissipated, but they'll observe similar mergers, measuring their properties, determining recoil velocities, testing whether kicks strong enough to eject black holes are common or rare. The future of gravitational wave astronomy will provide crucial context for interpreting Abell 2261's mystery, showing us whether the recoiling black hole scenario is plausible, likely, or perhaps even inevitable, given the right conditions. It will connect the distant past of one cluster to ongoing observations of gravitational wave events across the universe. The possibility of finding the runaway black hole. There's still a chance that the black hole is out there, wandering through the galaxy or beyond, and that we'll find it. If it's still accreting gas, even a small amount, it might emit detectable radiation. If it's surrounded by a concentration of stars, their combined motion might reveal the black hole's presence. If it's moving through gas clouds, it might create a wake, a disturbance in the surrounding medium. Astronomers are searching for all these signatures, looking in the places where an ejected black hole might hide. The possibility of finding the runaway black hole keeps the search alive. It's a long shot, perhaps, but not impossible. And if it's found, it will be one of the most remarkable discoveries in astronomy. Direct confirmation that black holes can be ejected, that gravitational wave recoils are powerful enough to fundamentally alter galaxies, that the universe is capable of even more extreme phenomena than we imagined. The meaning of Abell 2261's mystery. What does Abell 2261's mystery mean? On one level, it's a scientific puzzle, a question about the location and fate of a supermassive black hole. But on another level, it's more than that. It's a reminder of how much we don't know, of how the universe can still surprise us, of how objects we thought we understood can behave in unexpected ways. The mystery challenges our models, forces us to confront the limits of our theories, pushes us to develop new ideas, and it inspires wonder. There's something deeply fascinating about a missing black hole, about the idea that a 10 billion solar mass object could simply disappear, ejected from its home galaxy by the violence of a merger. The meaning of Abell 2261's mystery is both scientific and philosophical. It's a problem to solve and a story to tell, a chapter in the ongoing human quest to understand the cosmos, the story of creation and absence. Abell 2261 tells a story of creation and absence, the creation of a massive galaxy through countless mergers, the creation of a supermassive black hole through the coalescence of smaller black holes, and then, perhaps, the absence, the removal of that black hole, ejected by forces we're only beginning to understand. It's a story of extremes, of the most massive objects in the universe, of the strongest gravitational forces, of events so violent they reshape entire galaxies. But it's also a story of loss, of something missing, of an empty space where something should be. This duality, creation and absence, presence and loss, makes Abell 2261's story compelling. It's not just about what's there, but about what isn't. And sometimes, what isn't there is more interesting than what is. The story of creation and absence is written in the galaxy's structure, waiting for us to finish reading it. The beauty of a question still unanswered. There's beauty in unanswered questions. They drive us forward, motivate exploration, spark curiosity. Abell 2261's mystery is beautiful, precisely because it remains unsolved. We don't know where the black hole is. We don't know for certain what happened. We have theories, evidence, clues, but not definitive answers. And that's okay. Science progresses through questions as much as through answers. Each unanswered question opens doors, suggests new observations, inspires new thinking. The beauty of Abell 2261's unanswered question is that it keeps us looking, keeps us wondering, keeps us engaged with the universe's mysteries. One day, the question may be answered, the black hole may be found, or its absence definitively confirmed. But until then, the question itself is valuable, a reminder that the cosmos still has secrets, that there's always more to discover, that the journey of understanding is never complete. The endless curiosity that drives discovery. What drives astronomers to spend years studying a single galaxy cluster, to write proposals, analyze data, build models, search for a black hole that may or may not be there? It's curiosity, the endless human desire to understand, to know, to solve mysteries. Abell 2261 captures this curiosity perfectly. It's a puzzle, and humans love puzzles. It's a mystery, and mysteries demand to be solved. And it's beautiful, in its own way, not just visually, but conceptually. The idea that a galaxy could lose its central black hole, that gravitational waves could kick it out, that we might find it wandering through space. These ideas are captivating. They spark imagination. They make us wonder what else is possible, what other surprises the universe has in store. The endless curiosity that drives discovery is humanity's greatest trait, and Abell 2261, with its missing black hole and its unanswered questions, is a perfect example of where that curiosity leads to the edges of knowledge, to new frontiers, to mysteries waiting in the darkness, billions of light years away.